General Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome back. We're going to finish off talking about Newton's laws today. We'll do a few problems involving friction and drag. We'll talk about drag for a bit, and then later in the class we'll talk about gravity, and it should complete our discussion of Newton's laws for a bit, and then we'll have the midterm tomorrow, and we'll carry on after the midterm during the week. So in this animation, I'm showing you the orbit of the moon around the Earth. The main takeaway here is not the distance is not correct, but in these sorts of animations, something is kind of compromised in terms of reality. So in this case, the distance, the moon is way too close in this animation, it's not this close. But I want to kind of show you what's happening as the moon orbits the Earth. Think about the force involved. Think about the direction the moon's traveling, right? And think about the acceleration, right? And if the force applies in a certain direction, what does that mean to the acceleration of the moon, right? Gets you started thinking about gravity, right? So all these are applications of Newton's laws, right? So once, for instance, you know Newton's second law, that left-hand side, some of the forces, there could be different forces, right? So there could be gravity, there could be drag, there could be a spring force, right? So the different kinds of forces you will encounter, but you deal with it kind of the same way that we've talked about applying F equals ma, applying Newton's second law. So today we're going to talk about static and kinetic friction, the two types of friction you'll encounter. We'll briefly talk about drag, the thing that we kind of ignored when we talked about projectile motion, right? Dropping things, we ignored drag. And you'll kind of appreciate why we did that. It complicates things, but you'll see. And we'll briefly talk about Hooke's law, which involves springs, the force a spring applies when you stretch it or compress it. We'll talk about the law of gravity, right? Newton's law of gravity. And then we'll get into how you can actually, for yourself, calculate the value of g, right? So 9.8 meters per second squared. We took it as a given so far in the class. You don't have to take it as a given anymore. After this class, you'll know how to get that number, kind of theoretically. All right, let's go to our notes. We left off talking about this problem, right? So imagine you had kind of an incline like this, something that looks like a hill. And if there was an object, a little box or something on this hill, and you wanted to think about the friction, we took that little box and we put all the forces acting on the box, right? So when you are dealing with this sort of problem, you can put in the weight right away, fairly easy to do, right? So start from the center and go towards the center of the Earth, right? And so don't get confused by the fact that it's at an angle. The weight always goes to the center of the Earth, right? So find where the center of the Earth is, point that way, that's the direction of the weight, okay? We have the normal force, right? What we said was it's the surface, right? So when you push on a surface, the surface pushes on you back. That resistance, right, is what we call the normal force. Normal because it applies 90 degrees to the surface, right? So it acts that way always, normal to the surface. And then we have the force of friction, right? So it's static friction, meaning that this is not sliding, right? So if I take my paper clip, right, and then I'm sliding it across the page, then that's not static friction, that's kinetic friction, right? So when something's moving, right, because the surface of the paper clip and the paper, they're moving relative to each other, right? They're sliding past each other, and that is kinetic friction. But if you just place something and it just stays there, that's static friction, right? And so static friction, which way it points sometimes can be confusing, right? So we saw that crate problem, that the crate on a truck, and you can kind of see that it can be confusing, right? So like if I hold my paperclip and move my hand this way, right, the friction actually is that way, right? So when I kind of do something like this and move my hand across, the friction between the paperclip and my hand is actually that way because it accelerated that way, right? So we kind of get that from the acceleration. One of the tricks with static friction, if you are confused by the direction, just come here, right? Think about this parcel that's sitting on this incline and imagine if you can just turn off static friction, which way would this move? It would slide down, right? So then that means the static friction must be kind of pushing that way, upward and to your right, and that's what's holding it in place, right? The static friction. Now, if you had put it this way, right, then that wouldn't work, right? Static friction is not working that way. That would imply that it's actually helping it fall, right? That's not what it's doing. Okay, so once we have the forces in our free body diagram, we have a coordinate system, right? So I said this is to your advantage. To rotate the coordinate system is to your advantage. You don't have to do that. The advantage is you don't have to break up these vectors. The only thing you have to do is break up the weight vector into components, the y direction, the x direction, right? Okay, so we started doing this last time. We said we're going to sum up all the forces in the x prime direction. Force of friction is positive. The component of the weight that's in the x prime direction is negative. How do we see that? Well, think about how do I get from the center, right, the start of this vector to the end of the vector? Well, I have to come down in the negative y direction and have to travel in the negative x direction, right? And that's how I get to the end of the vector. This is negative. The x component is negative, right? We set it equal to 0 because we're looking at the case where this box or parcel doesn't accelerate, right? Okay, so then we're going to do the same thing for the y, right? So sum the forces in the y direction. Okay, what are those? Well, we have the normal force in the positive direction, positive normal force. And then, like I said before, the negative weight cosine of theta is equal to 0, right? So doing a little SOHCAHTOA, right, finding sides of a right triangle. Okay, a couple things to note, right? So one thing is weight. You know how to restate the term weight, right? You can say mass times g, right? Acceleration due to gravity. You can substitute and swap that out. The other thing is we have to kind of figure out the equation for friction, right? So from your reading, kind of seeing that the force of friction, static friction, is an inequality, right? It's not a normal equation you kind of see. It's not F equals ma. It's not weight is equal to mg, right? It's an inequality where the static coefficient of static coefficient, you multiply by the normal force, okay? So just be careful with this, right? So when you're looking for static friction, what this will tell you is the maximum number, okay? So it's not necessarily the current state of friction, right? Because if you have an object, your little paperclip, and if you very gently push on it, right, it's going to have a little bit of friction pushing against your finger, right? But if you push a little bit harder, then it's going to push back a little bit harder and a little bit harder. And then there's a point at which it cannot push any more, and that's what this is saying. There's a maximum number. So if you were to plot, okay, if you were to plot the force of friction that you get based on the force, let's say, applied, right? So you're pushing on an object and there's some friction. The plot for this will look something like this. It'll rise, 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 and then it'll fall, and then stay constant. Okay, so this part is the static friction part, and this is the kinetic friction part, okay? So once you get something to move, right, you push, 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 and then it kind of starts moving, then the force of friction, right, is to say force of friction static is this, right? But if you want the force of friction kinetic, that's equal to the coefficient of kinetic friction times the normal force. Kind of the shape of the equation is the same, right? It's the form it takes is the same. The coefficients will be different, right? So this coefficient is something you can measure in a lab, and it depends on which material is in contact with which material. Wood against wood, wood against aluminum, right? So different materials that are in contact with each other will have different coefficients of friction. And in a problem, either this will be given to you, right, in a typical physics problem sense, but in the real world, you would look this up on a table, right? So somebody would have done experiments against the material you're interested in, and you look up the coefficient, right? So the normal force, you always multiply, right, either case. But keep in mind, this is an inequality, right? So this is only telling you what this maximum number is up here, right? So don't just plug it in always to get static friction. Sometimes there's a roundabout way of getting static friction by applying Newton's laws, right? By summing up forces, that's how you can tell what the static friction is instead of just directly plugging into the equation, right? Just be aware of that. It's an inequality, right? So in our problem, what we're going to do is try to find the maximum angle that this hill could possibly have before static friction is done its job. It cannot do any more. It will lose the battle against gravity and this box will start falling, right? So if you did this experiment, right, we looked at a demo video as well, right? If you did this experiment yourself, and make an incline for yourself, put a box on it, and just raise the incline, there's an angle after which it'll just slide. There's no stopping it, right? So what we want to do is see, okay, what if the static coefficient is its maximum value possible, the best it can do? Well, how far can we push this, right? So how far can this angle go? So we're going to use it as an equation, right? But in reality, it is an inequality, but we're just looking for the maximum value. So we can plug that quantity into our equation. So doing some substitutions, what can we do? We're going to substitute, we'll use the x equation, right? So let me rewrite that. Is that the force of friction, we're going to substitute and say, well, it's the static coefficient of friction times the normal force, and then we have the weight and sine, right? So weight is mg, sine of theta is equal to 0, right? Okay, so we wrote the x equation. Let's rewrite the y equation. That has a normal force minus mg cosine of theta is again equal to 0. Okay, so make sure, ask questions. There's a thread going on, right? So Jericho and Kyla, they're watching the thread. Don't hesitate to ask questions if there's anything that's not clear, right? Okay, what I'm going to do is try to solve this set of equations. Let me rewrite them on my next page as you may ask questions while I do that. Questions so far?
One question we had was, wouldn't the normal force have some amount of force in the x as well? And I think they're thinking about, they didn't consider that we rotated our system.
So yeah, it's a good point. So yeah, if you didn't, I mean, this is an option, right? So if you didn't rotate your coordinate system, let's say you're using the normal standard xy coordinate system, then yes, the normal force has components in the x direction, right? And that is your call. You're not required, right, to rotate the coordinate system. The coordinate system is on you, right? You get to pick the coordinate system. The rules with the coordinate system are really only a few, right? The rules are, if you point x in a certain way, y has to be 90 degrees to it, and then z has to be 90 degrees to both of them, right? That's the rule. That's all there is. So, but that leaves the coordinate system is x and y pointing this way, or this way, or this way, or any kind of orientation you'd like, as long as you're following the fact that each of them has to be 90 degrees to each other, right? So yeah, so if you didn't rotate the coordinate system, that's your call, no problem. Then yeah, just be careful when you're doing F equals ma, you'd have to have components, right? Normal force has components. Okay, let's solve this. What I'm going to do is move the terms. So I get the mu s times n is equal to mg sine of theta. Make sure you're following and kind of doing this yourself, right? Because as I do algebra, I could miss something. I could miss a minus sign, right? So don't just write it down. Be checking me as you do it, right? So normal force is equal to rewriting this equation, mg cosine of theta, right? And you might remember this trick from your math class. You can take two equations like this and divide them as long as you divide each side by each side, right? So you can divide this side by this side by this side, right? It's a little trick you can remember to use so that the normal force cancels out like this, the m's cancel out like this, the g's go away, and then you probably remember, right, sine divided by cosine is tangent of theta, right? A little trig property for you, right? So what you're left with is that you have the tangent of theta is equal to mu s, right? So very interesting result, right? Because what you're getting is the angle has something to do with the coefficient of friction, and that's it, right? And even though a lot of detail went into it, and this is kind of cool that it only depends on one thing, one quantity, right? So if you solve for that angle, you take the arctangent of the coefficient of static friction, right? You can get the angle, right, if you know the coefficient of static friction, or if you don't know the coefficient of static friction, you can measure the angle and actually calculate the coefficient of static friction. Right? So either way, so maybe you know this, maybe you looked it up on a table, or you have some new material that nobody's ever seen before and you just created it, and then all you have to do is do this experiment, right? Do this experiment, measure that angle precisely at the point where it starts to kind of start sliding, just like we saw in that demo. Then by knowing that angle, tangent of that angle is your coefficient of static friction. Other questions coming in?
Oh, we got a question. Is the mu coefficient for kinetic friction always less than the static friction?
Kinetic versus static?
Yeah.
Yes, good question. Yes, usually yes. There might be some materials that's, off the top of my head, I can't think of something, but usually this is the behavior is that the static friction, the maximum value is higher than the kinetic value, right? For the same normal force, right? If you look up the static coefficient versus the kinetic coefficient will be smaller, right? And the other thing is what you can do is actually do this experiment yourself. My water bottle is kind of heavy, so this particularly works with something heavier. So if you put something heavier and you try to move it, you can kind of feel this yourself, because if you try to push, it pushes back, right? So because the static coefficient is there, right? And if you push harder, it pushes back harder. And then if you push just enough, it starts sliding. That means you've gotten to the maximum friction, static friction, right? But once it starts moving, you'll notice that it's actually easier to keep it moving than it was to get it to move in the first place, right? Like especially if you have a heavy box or something, you're moving, it's on the ground. If you push, it feels like you're doing a lot. But once you get it to move, it feels like, okay, this is not as bad, right? And it's because the kinetic friction is lower than the maximum. However, notice that static friction can be extremely small, right? Because if you're only pushing very, very gently, the static friction that's generated is really, really small, smaller than the kinetic friction is, right? But yeah, if you're comparing the maximum to the value, because kinetic friction is the same value, right? It's not an inequality. It's just the same throughout. Once you get it to move, it's just the same amount of friction. But yeah, that's a good question. Other questions about friction? Good. Anything from you all? Good. All right. Cool. So that's a little kind of brief overview of what friction is. You kind of know what you need to know. There are two equations, right? These are the two equations. two types of friction, static and kinetic, right? So we will move on to talk about a different force, and that is the drag force, right? And this is what we left out when we talked about projectile motion, okay? And one reason is there are two kind of equations for this, right? For one, let's look at the first one first. And the first one is the force of drag is equal to 1/2, some coefficient, we'll talk about that, rho a v squared, right? So lots of terms. What do they all mean? Okay. So the c here, this coefficient, is the coefficient of drag. Okay. It's something you have to measure. You have to put an object into a wind tunnel, for instance, and measure this. For the coefficient of drag for a flat plate, okay, imagine a flat plate is aimed right against the wind, right, in the direction where the area is largest against the wind, then this value is 1 for that. Kind of, it's like a worst case scenario in terms of drag. If you think about the coefficient of drag for a car, for instance, it's about 0.3, just to give you kind of a reference, right? So a car is better designed than flat plate, right? So if you make a box, literally, right, like a boxy car, that's not very aerodynamic, right? It's going to be pretty large drag involved, right? So you want to make it kind of streamlined, kind of like a sports car, kind of, you kind of get that shape, or an airplane, right? They're designed to reduce drag, right? You don't want to have a high amount of drag when you're trying to fly through the air or drive through the air, right? Okay, so the other one, rho here, this is the density of the medium you're going through. It could be water, right? There could be drag if you're swimming, right? The drag is coming from the water. If you're trying to fly an airplane, that's air, right? So that's density. The A here is area, okay? And that's the area that the kind of the wind sees, right? So it's kind of the front view. If you look at the airplane, if you look at it from kind of the side of the nose, like staring at the pilot kind of view, right? So that's what you mean is the area. So, or a car coming right at you, like facing the car. So the area there, right, is what we're concerned about. And v is velocity, right? So it's really speed. We're not really particular about the direction, because we kind of know what the direction is, right? So one's moving one way, you're going against the flow of air, right? Okay, so the scenario is kind of like a car, right? So if you think about a car, bad design looking car, you can draw better cars. Okay, so there's a car, let's say it's moving to your left, right? And the wind, right, the air is going to be kind of coming at it this way. So the airflow is like that, right? So the velocity is kind of relative velocity against the wind, the air, and the area is from the perspective of the air, what is the area of this car? It's not this area, it's not the side, right? It's kind of the face-on area, density, coefficient, and there's a 1/2, okay? So this equation, this one is for large objects going relatively fast, okay? Think cars, think airplanes, right? Large objects going relatively fast, this is what you want to apply, okay? But if you're in a lab setting, biology lab, chemistry lab, right, so you might be dealing with dropping certain things into a fluid and it's moving relatively slow, it's a small object, so then you use something else. It's called Stokes' law. Okay, and it's still drag, but just to distinguish, I'm just going to say Fs for Stokes, right? And that's going to be 6 pi r eta, Greek symbol eta, and velocity, okay? Again, we'll go over what the terms are. 6 pi, those are numbers, right? The r here is radius, right? Think about dropping a small bead into oil or something like that, right? So what's the radius of that bead? This eta, Greek eta, is the viscosity of the fluid. What's viscosity? It's not density, so not to be confused with density. Density is how much mass is there per volume, how much stuff per volume, right, is density. Viscosity is a different idea. Viscosity is about how fluids flow, right? So think about pouring water versus syrup, right? If you're putting syrup onto your pancakes or something, it's very kind of viscous is the term. It's kind of slowly drips over, right? As opposed to water, if you pour water, it easily flows, right? So the viscosity of water is less than, let's say, syrup. Okay, that's what we're after. V, again, is for velocity here, right? So we have V for velocity. Notice that the velocity goes as squared here, but the velocity goes just V here, right? And this one, right, for this one's good for small objects going relatively slowly, okay? So imagine the kind of the typical thing I would think about is kind of dropping a bead or something really, really tiny into a beaker, right? Some test tube, right? That sort of situation. Something small going relatively slow. You want to apply Stokes' law, right? So why do we have two? Well, this works better for its own scenarios. For cars and airplanes, this works better. It represents drag better. But when you're dealing with small objects, this works better, right? So it's a little messy. You don't have one equation that explains everything. You have two usually that you deal with, right? So depending on the scenario. Now, earlier we looked at the case of going skydiving, right? So without drag, if you jump out an airplane, you'll go faster and faster and faster and faster and faster, and you're going fastest just before you hit the ground, right? Because you keep accelerating the whole time, right? If you didn't have drag, you would just go faster and faster and faster and faster, and just before you hit the ground, right? You don't want to hit the ground, but if you hit the ground, you're going really, really, really fast, right? But in reality, if you did go skydiving, you don't just continuously get faster and faster and faster, and that's because of drag, right? So let's look at that. Look at that now, where you can see that you don't just consistently just get faster and faster and faster. You do get to a point where you don't go any faster, okay? So we go skydiving. Okay, let's think about you and what's working on you in terms of forces. Certainly have your weight pulling down, or the earth is pulling down on you. Okay, this is you. Right, and what else is acting now? Right now we have the ability to include drag, right? Drag is pushing against you, right? So if we did our F equals ma, right? So we sum up all the forces on you and set it equal to ma, right? What we'll find is that as you go faster and faster and faster, what's happening to drag? You're a relatively large object going relatively fast because you're going skydiving, right? So then the force of drag that you want to use is the first one, right? 1/2 c rho a v squared, right? Notice what happens to this drag as you get faster and faster, right? So if you're not moving at all, then the drag force is 0. But as you move slowly at first, but then faster and faster and faster. And notice this is also squared, right? So the faster you go, it's just this and squared, right? So it's a larger number. This drag gets very, very large, right? So at some point, you can imagine that this force is large enough to be equal to your weight itself. Not initially, right? When you just jump off the airplane, right, your weight is significantly higher than the force of drag, so then therefore you fall down, right? You accelerate into the ground. But after some time, right, well, after your velocity has gotten fast enough, you can imagine this number could be as large as your whole weight, okay? At that point, what you have is a situation where when you do the sum of the forces, you have, yes, your mg plus your drag force, and you'll get the condition where the right-hand side is 0. You will stop accelerating because when the two forces are the same, right, they sum together to be 0, okay? So what you get to is this thing called terminal velocity. Okay, you get to a terminal velocity that for a typical person, right, what is terminal velocity? Is about 218 kilometers an hour, or if you like miles per hour, it's about 135 miles per hour, depending on kind of the numbers you use, right? So you can do this yourself, right? You can use your own mass, right? Measure your mass. You know the value of g, right? Roughly 9.8 meters per second squared. Then for a person, right, try to estimate the coefficient of static friction, right? So you can look this up or make an estimate. It's not 1, right? Is it good as a carb? Is it 0.3? Probably close to 0.3. Okay, maybe use 0.3. Density of the air you can look up. The area, the cross-section of your area, right? So you can estimate, maybe stand on the ground, right? Use a ruler and measure your cross-sectional area. And you can solve for V, right? You can solve for your own, I just threw some numbers that are kind of approximately like a human, you know, rough estimates. So I get this by kind of putting in some reasonable numbers. But do this yourself, come up with your own number for terminal velocity. And you can come up with, if you were to jump out of an airplane, right, this is without involving a parachute at all, what's the fastest you can get going just because you're falling to the ground, right? You have gravity and the force of drag acting on you, how fast will you get, right? So this is slower than if you treated yourself as a kinematics problem, right? Now contrast this with at a certain altitude of an airplane, you jumped off the airplane, there's no drag, there's no parachute, how fast would you be going when you hit the ground? That number is going to be much larger than this, right? So you're going to be getting to the ground much, much faster, right? So do that, get an estimate for terminal velocity for you, roughly in the ballpark of like this, 135 miles per hour. How are we doing questions-wise? Doing good?
They're kind of like stuck on the terminal velocity, like how they stop accelerating once they reach the terminal velocity.
That's the question?
Yeah, they're asking like, why is the sum of forces when you're skydiving equal to 0?
Oh, yeah. So let's go back to the notes. So the argument here for this is that there are two forces. Hopefully everybody kind of sees that, right? There are two forces, weight and the force of drag, right? And this is kind of abstract, right? How much weight, how much of force of drag do we have, right? We're using the large objects going relatively fast because you're not a bead, right? Like you're a relatively large object. So the drag equation that works better for you is this one, right? So 1/2 and, you know, coefficient of drag, density, that sort of thing, right? So the argument is that, yes, when you're not moving, barely moving, you just stepped out of the airplane, you're barely moving relative to the ground, let's say, right, vertically, then this is almost 0, right? The force of drag is almost 0. But as the velocity, right, this number gets larger and larger and larger, one can see there is potential for this to be equal to that, right? And that's in fact what happens, where this number, right, it will get large enough to the point where it's equal to the weight, right? So when you do the sum of the forces, you have the weight, mg, you have the force of drag, and there is a point where they will equal each other. And the thing is, you can do this as an experiment, right? You can measure this, and you can see that, yes, objects that fall in the air don't just keep accelerating all the way down to the ground, right? So at some point, if you have sufficient height to work with, right? So if you're dropping over some significant height, you get to the point where these two forces will equal each other. And then when two forces are equal to each other, then there cannot be an acceleration, right? So that's why you get to a terminal velocity where there's a certain velocity where it doesn't get faster any faster than that, because then it wouldn't make sense, because it cannot, because if it's a little bit faster, that means the drag force is going to be larger than the weight, right? So there's no point where you will start levitating because of drag, right? That's not going to happen. So it just gets to the point where this equals this, and then that's it. These two forces will stay the same all the way, the rest of the way down to the ground, right? Is that maybe the question, sort of? Okay. Okay, getting an overview of all the forces, right? So we're not going to get into a lot of detail with a lot of the forces. We don't have time. But if you're interested in any of these forces, right, it's more relevant to your profession, your career. You want to know more about it, right? You may deal with drag. You may deal with friction, right? So it depends on what you're interested in. You can do some more digging, right? So do additional reading. There's more information in the textbook and online, right? We just have time to go and do a brief overview, right? Okay, so talked about drag. The next thing we want to talk about is the spring force, called Hooke's law. So if you dealt with a spring, you know it can generate a force, right? So imagine I have a spring like this. And what I'm going to do is pull it apart, right? And from experience, if you've dealt with the spring, if you try to pull apart a spring, what does it want to do? It wants to compress, right? It wants to go the other way. So when you do this, what the spring wants to try to do is to pull itself back together, right? So the force of the spring, right, it's in the direction that tries to compress itself, right? If you try to stretch it. Now, the opposite also is true, right? So if you took a spring, right, and did the opposite where you compressed it, right? So if you tried to squish it together, what does the spring want to do? The spring does the opposite, right? It's tries to resist it, right? So it's kind of rebellious. It wants to do the opposite of what you're doing to it, right? So if you stretch the spring, it wants to stretch itself back to the smaller length. If you compress the spring, it tends to want to stretch itself back to its original shape. It likes to be at a certain kind of original length of it, right? So the way you'd write this in terms of an equation is the force of the spring, right, still vector, is equal to the negative, meaning opposite, of the displacement. So there's a spring constant, right? So that's a constant that you need to measure. It depends on the spring you're dealing with, right? Each spring, different materials will have a different spring constant. And then you have a displacement, right? Remember displacement from earlier in the class, okay? So depending on your displacement, your friction will be the opposite, okay? So if you stretch out the spring, you call that displacement positive, then what this is saying is the force is in the opposite direction. The negative saying the opposite, right? If you compress it and you consider that compression, the displacement is negative, negative becomes positive, so then the force is the opposite in the positive sense, okay? So the negative's just to indicate it's always going to be fighting whatever the change is, right? If you compress it, it wants to stretch back out. If you stretch it, it wants to compress itself, right? So it fights kind of any kind of changes. It resists that, right? So that's the spring force. We'll get back to springs later in the class. Just kind of a quick overview of springs right here. We'll talk about simple harmonic motion, oscillations, and then we'll kind of deal with springs once more. They're kind of useful. You can model a lot of things as springs. It seems like a simple object that is, again, no big deal, but you can model a lot of things. I mentioned the normal force can be modeled as a bunch of springs, right? So if you have a surface like your table, imagine your table is made out of a bunch of springs, and that normal force you feel when you push down is kind of like this, right? Because you're trying to compress the spring, right? You're like your table, if you imagine it's made out of a bunch of springs, you're trying to compress it, then it tries to stretch itself back out, right? It starts to push. So you can model materials as a bunch of springs. You can do other things with springs. So very useful object. So it seems pretty simple, but it's actually quite useful. All right, the last force we're going to deal with today is gravity. We've dealt with it before, but now we're going to look at some specifics of how to calculate the force of gravity, right? Once we do that, we'll do a couple of Instapols, and after that we can talk about anything related to midterm 1. If we have questions about concepts, we can go over them, and we'll take questions about that. Okay, so Newton's law of gravity, we're going to look at a model that was the original idea of what gravity is, right, in terms of an equation. It's not the most complete model of gravity, right? So if you want a better model of gravity, look at Einstein's law of gravity, right? It's called general relativity. It's a lot more complicated. It's more complete, but it's also more complicated. So if you want to talk about black holes, right, you want to talk about the entire universe and how it behaves, you need the more complete form of gravity to deal with situations like that, right? But if you want to understand, let's say, the orbit of the moon around the Earth, right, you want to send Apollo astronauts to the moon, that's all you need, right? So it's not to take anything away from Newton's laws. It's not the most complete, but it's actually very powerful, right? So, and also easier to understand what's going on, right? So when you have two objects, what's happening in terms of forces. So let's take two objects, 1 and 2, right? Two objects. And Newton's law of gravity says that if there are masses, m1 and m2, just because they have mass, right, it's a property of mass, they will apply forces on each other, okay? So this one will tug on this one will tug on this one. They will apply forces on each other, right? And we're going to need a little subscripts here, otherwise it's hard to keep track of who's doing pulling and pushing. So I'm going to say this m2, right, so the force on 1 by 2. Okay. How specifically I use the subscripts is not that important, right? So if you want to say it slightly differently, A and B, A on B, the order how you list this is not important. It's just to have some system that makes sense to you. The issue is to say this one is pulling on this one's pulling on that, and you want to keep track of who's doing the pushing and pulling, right? Okay, so force on 1 by 2, and the force here is going to be force on 2 by 1, right? They are going to pull on each other. and we have a certain distance between them. Call that r. That's going to come into play. That's important. Okay, they're some distance apart. And we're going to use some unit vectors to keep track, okay, of directions. So this, and it has a unit vector r hat 1 by 2, right? So the direction of the force on 1 by 2 is that way. And then we have another unit vector pointing the opposite way. Remember, the unit vectors are very good at keeping track of direction, because if this is the Earth, if this is the Moon, as they go around each other, the forces are going to change directions, right? So it's not a static situation where things are just staying in place like this. If you're talking about the Moon would be moving, and the two forces would be pointing in a different direction, right? So you need unit vectors to help you with this, right? Otherwise, it's really hard to keep track of all the directions. So how does the law go? The law goes as the force on 1 by 2 is equal to big G. It's a constant. We'll talk about that in a second. m1 times m2 divided by r squared. R hat 1, 2, right? So the r hat is keeping track of the direction, right? This is a force, it's a vector, and therefore it needs a direction, right? Notice that all the numbers in here are scalars. G is a constant. What is it, right? So you can look up the value. It's a universal gravitational constant, 6.67 times 10 to the minus 11 newtons meter squared divided by kilogram squared, right? So the units are just to make sure everything works out, and on the left hand comes out newtons, right? So that's a number, right? Mass is a number. The two masses are numbers. The distance squared is also a number, right? So you can look up the value for the distance from the Earth to the Moon, for instance, and that's also a number. So none of these things are telling you a direction. So we need a direction, and that's why the unit vector is very helpful. It tells you which way the force is going, right? Now, we can also write it for the other one, right? We can write that the force, use a different color here, so force on 2 by 1 is equal to, again, G, if you want to switch M to M1 here, that's fine, but it's not going to do anything in terms of math, right? It's the same thing, r squared, and the unit vector is 2, 1. Okay, so these two will tell you what these forces are, right? Between the two objects, this is what you need to do, is to get the force, right, in a particular direction, right? Doing okay? Hopefully, right? So just don't worry about, kind of don't miss out on the unit vector here, right? Just to point out, if you had a vector, right? Do you want to pick a letter? Pick a random letter. H, okay. So we have a unit vector H. Well, sorry, you have a vector H, okay? Some vector, just giving you an example, right? So some vector H, and what we can do is come up with a unit vector, right? Remember, a unit vector points in the same direction as the vector itself, but has a length of 1. So the unit vector is h hat, right? So the vector itself, right, if you want to say h, you can say h, but you can also say the same thing by saying h magnitude times h hat. Does that make sense? Right? So when you have a unit vector, right, you can kind of outsource the direction keeping to the unit vector and say, hey, why don't you keep track of direction? H will keep track of the length. Right? So the magnitude, right, it could be 10, it could be 100, right, whatever. You're separating those out, right? You're saying, oh yes, this is the vector, right? This is the complete vector. H, right, is the vector. But instead of just calling it h, you can actually do it in this way, where you're splitting the two parts, right? You're saying one is the magnitude, one is the direction, And it's oftentimes very helpful to break up a vector into kind of pieces like this, where one part is the magnitude part and the other part is the direction part, right? So any vector, right, anything, I can make up a vector h, right, like I did, and h, the vector, could have h hat, right, its unit vector. And once you know its unit vector, which points in the same direction as h, all you have to do is multiply by h, the number, the magnitude, the length of that vector, by h hat, and it gives you h, the vector, right? Does that make sense? So you're familiar with now the unit vectors that are always connected to our coordinate system, right? So we have x, y, and z, right? And you've now seen there are unit vectors that point in the direction of x, in the direction of z, and the direction of y, right? And we gave them special names. We said it's I hat, this is j hat, this is k hat, right? So the unit vectors associated with the coordinate system, they're not the only unit vectors, right? They're very special, they're very handy, right? The I, j, k unit vectors are very useful and very handy, and they're always stuck to those coordinates, x, y, z. They don't just float around, right? They're not just kind of for anything. However, the concept of a unit vector, right? A vector that points in the same direction as the vector itself, but has the length of 1 in whatever units the vector is in, length of 1, that is a more general idea, and it's kind of useful for other purposes, right? Okay, so let's use Newton's law of gravity to understand where that number g, little g, not big G, but the little g you've been using for kinematics comes from, right? So let's say you have a mass above the ground, and let's say you're on the moon. You're going to ignore air resistance. Let's say you're on the moon, and the only force that's acting on it is the force of gravity, right? And so now you know how to do this, right? So sum up the forces is equal to ma, right? Now the force, what's the force? What's the net force? Well, we know now what it is, right? So it's big G. I'm going to use big M to represent either the moon or the earth, right? So the massive object this is on, and then little m for that object itself, and then we're going to divide by r squared, right? Now, I know the direction. I'm going to ignore the unit vectors because I know which way this direction is, and it's not going to change once it falls, right? As it falls, the direction of the vector doesn't change, right? It's always downward. And r, remember, it's the distance between the centers, okay? So if this is the Earth, and this is your small object, right, that this is, then what you need is the distance from the center of the Earth to the center of that object. So when you're talking about that distance, it isn't this distance to the surface, right? So now we have to be a little bit more careful, right? The more complete, right? The law of gravity is about two masses, but when you want to try to find the force between those two masses, you need from the center of one to the center of the other thing, right? Okay, so we can put those numbers in, right? So then, okay, so this is the force, right? That goes on the left-hand side. The acceleration we're looking for is g, right? So acceleration due to gravity is what we're going to try to solve for, right? So plugging these in, what do we have? We have big G, big M divided by r squared is equal to m times g, right? And here is where the hammer and the feather comes in, right? Why? Because notice what happens. The little m goes away, right? So when you solve for g, when you say g is equal to big G, universal gravitational constant, right? It's a constant of nature, right? also shows up in Einstein's gravity, right? That same number shows up in Einstein. So it's a fundamental constant. Then you have the mass of the big object, let's say the Earth, the Moon, what have you, right? And the distance squared, right? And that's how you get g. And it has nothing to do with the little object, right? That mass could be a feather, a hammer, doesn't matter, right? The mass of that object does not come into play when you're talking about the acceleration due to gravity, right? This is a fundamental thing. Like the people before, they couldn't understand this, right? So thousands of years ago, if you dropped a feather and a hammer, the hammer will fall first, right? So then people had this misconception that, oh, the mass had something to do with the falling, but the mass has nothing to do with the falling, right? This mass, right, the rate of it falling has nothing to do with that, the particular little m, right? It goes away. So if you can imagine this on Earth, right? So let's draw the Earth. Here's the Earth. Kind of odd shape, but you get the idea. And we put U, right, stick figure U. You have a little ball in your hand, right? And you're about to drop that ball, and you want to figure out, okay, what's the acceleration due to gravity? Of course, this is completely disproportionate, right? The Earth is very massive. You're not this tall, right? But it gets you the idea, right? So what do we need? We need the distance from the center of the Earth to the center of this object, right? So technically, we need this distance, right? But because that distance, right, from your hand to the surface is such a small number compared to the radius of the Earth, we're just going to say this is the radius of the Earth, okay? If you want to really be precise, you can take the radius of the Earth and put that height in, but it's such a small number, it's not going to make a difference, right? So, I mean, this is a small number. The radius of the Earth is a giant number. The radius of the Earth is actually 6,378. I'll give you some decimal places here. Kilometers, right? So 10 to the 3 meters. As I said before, big G is 6.67 times 10 to the minus 11 newtons meter squared kilograms squared. Mass of the Earth, right? Maybe I just want to do it for the Earth, is 5.9722 times 10 to the 24 kilograms, right? So once you take these numbers, put it into this equation, right? Do it yourself, see what you get. What should you get? Think about it. What should you get? You know the number, right? What should you get? What do you expect to get?
9.8.
Yeah, you should get something like 9.8 meters per second squared, right? So now you have the equation, right? So before we said, okay, you can do some experiments to measure the acceleration due to gravity, right? That's all you could do to get 9.8, and you say, okay, that's a constant, and you're going to use it for kinematics problems, right? But now you have the theoretical basis of where the heck that came from, right? It comes from the law of gravity, right? Newton's law of gravity. You're applying Newton's second law to it. And then you can calculate the acceleration due to gravity based on fundamental constants, right? So big G, the universal gravitational constant, the radius of the Earth, right? You go there, square it, be careful with the kilometers, right? And making sure, so these are standard units, so it should be fine, but make sure you're squaring it. And you should get roughly 9.8 meters per second squared, right? And the other thing you can do is calculate what G should be at the International Space Station, right? So take the radius of the Earth, add the altitude of the International Space Station, and figure out what the value of G is, right? And you'll see it's smaller than on the surface of the Earth, but it's not 2. It's not 0, right? That's the point. So you're going to get a number that's, yes, is smaller than 9.8 meters per second squared, but not by as much as you might think, right? So do that as an exercise. Try to calculate what is the value of G at the International Space Station. And then you can see the weight, right, of a astronaut still there, right, because G is still there. Questions so far?
A lot of them are confused about setting up like the gravitational equal to your mg and like which ones cancel out of the masses.
Oh yeah, sure. So going back here, right? So F equals ma. Ignore the right-hand side first. We want to sum up the forces on this object, right? So the only force we're going to consider is gravity, right? Here's the formula of gravity. G, constant, right? Big G, I know there are two different G's, so just be careful. Big G is a constant of nature, right? This is a universal number. The little g depends on the planet you're on, right? How far you're from it. This is not a universal thing, right? So we need big G, we need two masses, M1, M2, right? From before we had this, right? So you always gravity, at least you need two objects, right? For there to be a gravitational force between the two. So two objects, M1, M2. Instead of calling it M1, M2, sometimes you want to call it big M and little m because one of them usually is larger than the other. The big one could be the Earth, could be the Moon, wherever you're dropping an object from, right, is the big M. Little m is the mass of the object, right, which you need because they're attracted to each other, right, they exert a force on each other, and then distance squared, right, r squared, is from the center of this thing to the center of the Earth or the Moon, right. So that's the force. On the right-hand side is ma, generally ma, right, we've seen before. Mass is the object you're concerned about, right? You draw a free body diagram of this thing, so that's the mass you're thinking about, right? Mass of this object, right? Because it's the free body diagram was about this, right? We weren't looking at the acceleration of the Earth, and if you did this for the Earth also accelerates upward, right? Which is maybe strange, but it does do that. If you drop an object, yes, the object accelerates down towards the Earth, but the Earth also accelerates upward towards this object. But the Earth is extremely massive, so you're not going to really measure that, right? It's not going to move by a whole bunch. It's such a small quantity. But if you want to calculate it, you can do it. Just do the free body diagram for the Earth instead. Use the mass of the Earth here, and you'll get the acceleration of the Earth, which is a tiny number. So focus on this, little m. A is the acceleration. We label it as g because the acceleration we're talking about is acceleration due to gravity, so oftentimes just called g. Putting everything here, we have the force of the gravity here, and we have mg over here, and the two m's, right, the little m's will cancel, meaning that this mass doesn't appear when you're trying to calculate the acceleration due to gravity, right? It's this mass that cancels out. The only mass that's left is the Earth itself, right? The thing that's causing this to accelerate in the first place, that is still there, right? So, or if you're doing this for the Moon, you can put the mass of the Moon, right? All right, let's do some practice with some Instapols. See how you're doing with this. Let's switch over to the computer and I'm going to send you an Instapol. All right, take a look at this and maybe take a minute to think about it and we'll come back. Okay, so answers coming in. Give you a little bit more time to throw in if you're just about to put in your answer. Okay, the Earth has about 80 times the mass of the Moon. The gravitational force exerted on the Moon by the Earth has what relation to the gravitational force exerted on the Earth by the Moon, right? So what's the relationship between the two forces, right? One on the other, right, and vice versa. Is it 0? Is it the same? Is it 80 times? Is it 1 over 80, right? What's the answer here? Say what we have. Okay, so same is winning out. 80 and then 1 over 80, I think, kind of next popular answers, right? So how do we figure out, right, what this is? Let's go to our notes. We want to consider how gravity works, right? If we have two objects, this could be the Earth, this could be the Moon, and we want the forces, right? So if you want to calculate the force, let's say, that is the Earth applying onto the Moon, this one, right? 2, the force on 2 by 1, right? So that's that way. That's the Earth tugging on the Moon that way. Well, how do we do that? Well, we use this one, right? We use the two masses divided by the distance squared, right, in a certain direction. Now, if we want the other one, we want the force on 1, right, by 2. So let's say the Moon tugging on the Earth, right, to the right. Then we use this one, right, to figure it out. Now notice that all you're doing is swapping out the masses, right? That doesn't do it, right? So 2 times 10 and 10 times 2, there's the same thing, right? So if you multiply two numbers in different order, that doesn't matter, right? So everything in here and everything in here is the same number, right? So nothing's different, right? The gravitational constant is the same. The two masses that appear in different order doesn't matter, right? And the distance, right? The distance we want the center of the Earth to the center of the Moon. That distance doesn't change with the two different forces, right? So they're the same because the gravitational force acts this way, right? We have an equation that tells us how to calculate it. There's another way that even if you didn't know this, right? Let's say you didn't know such a thing existed, right? This person came up with 3 laws, that there's another one in the 3 laws would help you say and answer this question even without knowing this was there. Of course, use it because you know it's there. But even if you didn't know the law of gravity, you could have answered this question using which of the laws? Yeah, right. So Newton's third law, right, is built into Newton's law of gravity. Good, because the same person, right? So that would be bad if he didn't incorporate it. The third law is built in already, right? So if the Earth tugs on the Moon by a certain amount, some force, then the Moon tugs on the Earth by that same force, only in the opposite direction. Right? The magnitude is the same. So if there is a force, right? That's why the third law it sounds very simple, but it's actually quite profound, because if you apply a force on an object, you do some pushing on some object, that object will push you back. It's not optional, right? So it comes in pairs, action, reaction, pairs. It comes in pairs. And you can see it works for gravity, right? It works for you pushing on the wall, for instance, right? It comes in pairs. And so Newton's third law, very, really, really important idea, right? Okay, one more instant poll, and then we'll switch over and talk about midterm stuff, anything that you want to discuss about the midterm. Okay, let's do one more. Send this your way. And if you hear some construction, sorry, apologize, it's next door. Hopefully it's not too bothersome on the audio. Okay, so I'm going to zoom in on this, right? So there's not much of a question prompt here. The Moon does not fall to the Earth because, and you have several options to choose from, okay? So you have these options showing up on your side, right, on your device. So I'm not going to kind of zoom out. So I'm going to leave it zoomed here. Consider your choices here. The Moon does not fall to the Earth because, right, go through each one, see what you think. Ask us questions on a discussion while we do it. Let's take a minute and a half, think about this, and we'll come back. Okay, how are you doing? Yep, getting some answers in. Let's take a quick look. Right, you have several options here to choose from. Let's see, what do we have so far? Okay, we do have a breakdown, quite a variety of choices here. Right, oop, should not stop that. Okay, so as you can see, distribution of different ideas of what's going on, right? So, okay, let's go through it one at a time, see if we can figure it out. Moon does not fall to the Earth because the moon is in the gravitational field of the Earth, right? The moon is in the Earth's gravitational field, right? Is that the reason why the moon does not fall to the Earth, right? Think about what if I hold up an object. Let's switch to the camera here. So here's my paperclip. If I'm holding up my object, this paperclip is in the gravitational field of the Earth, right? But if I let go, it falls to the Earth, right? So the moon's in the gravitational field of the Earth. It doesn't do that. It doesn't kind of come down to the ground, to the surface, right? So it's not the first one necessarily, right? That's not the reason why the moon does not fall to the Earth, because if it's just gravitational field, a lot of things just fall to the Earth, right? If you let go of your water bottle, it'll fall to the Earth. It doesn't go around the Earth, right? Now, the net force on the moon is 0. Is that true? What are the forces on the moon, acting on the moon? Let's switch over to the dot cam here. So Instapoll 2, right? So hopefully you're drawing a picture when you see these sorts of questions, right? So we can think about the Earth. Here's the Earth. And put the moon going around it. So here's our moon going around the Earth, like that. Okay. So when you look at the moon, right, so what are the forces acting on the moon? How many do we have? If we're just considering Earth and the moon, right, if we're going to ignore the sun, we're going to ignore Jupiter for a second. Sorry? Yeah, which one? What's the force acting on the moon? Yeah, just the force of gravity, right? Gravity is acting towards the Earth. So once the moon moves over here, here's the moon, which way does the force go? It's, again, towards the Earth, right? That's the force of gravity, right? So that's the force acting on the moon. And the net force is not 0. There is a force acting on the moon, right? There's nothing to counter this force, right? There's no normal force. There's something else to counter it, right? There's just one force, and it's there, right? So the net force on the moon is not 0, right? There's a net force on the moon. Okay, then going to the next one, the moon is beyond the main pole of Earth's gravity. That's not true, right? I mean, it's in the pole of the Earth's gravity. As you can see from the gravitational equation, right? For the force of gravity to be 0 between any two masses, technically speaking, it has to be infinitely far away, right? That's the only way you're going to get the whole thing to be 0. If something has mass, something else has mass, right? So if you're talking about the Earth and the moon, those two objects will exert a gravitational force until you take them infinitely far away, right? Now, in practice, you don't have to do that, right? So a spacecraft, for instance, that you launch from the Earth, it doesn't have to be infinitely far away from the Earth to kind of basically not really feel any gravitational effects from the Earth. So there is a kind of a point where it becomes approximately 0, right? So if you send a spacecraft to Jupiter, the spacecraft is more affected by the gravity of Jupiter than the Earth. The Earth's number is extremely small at that point, right? So in practice, you don't have to really go to infinity, but in theory, yeah, it has to be, it's there still, right? Some effect is there. So it's not that the moon is beyond the pull of the Earth's gravity, right? So that's not it either. The moon is being pulled by the sun and the planets as well as the Earth. That is true, right? The moon is being pulled, right? So anything with mass attracts anything else with mass, right? So the moon has mass, the sun has mass, so the moon and the sun will pull on each other, right? Also the planets. So if you're really trying to make a simulation and you're trying to model the solar system, you really have to account for all of these things, right? But it still doesn't explain why the moon goes around the Earth, right? Okay, so what? There's a force, right? So what's the answer? If it's none of these things, what's the answer? Zoom out. We're changing our minds, hopefully. What do you all think? What's the answer?
Is it because the speed of the moon is keeping it from going towards the Earth?
Yeah. So there's a quote in the Hitchhiker's Guide. If you've read the Hitchhiker's Guide or seen the movie, it's probably not in the movie. I think it's probably just in the book. But there's some joke about the fact that the trick to flying is to jump off a hill or something and miss the ground or something like that. There's a quote, if you've read The Hitchhiker's, you probably can throw it in the ed discussion if you remember the quote, if you've read Hitchhiker's Guide, the book. But it's not too far from the truth in the sense that, yes, the moon is falling towards the Earth, but it keeps missing the Earth, right? That's why it is able to go around the Earth. So let's go to our notes and think about this again, right? So here's the Earth one more time. Here's the Earth. And let's put the moon right there, right? So here's the moon. Why doesn't it fall? It does fall, right? So if it wasn't moving sideways, right? If it didn't have a velocity already, it would just crash to the ground. Right? Anything else, right? Like if you hold up anything against the ground, it will fall to the ground. And if the moon hadn't a velocity, right? It wasn't moving sideways, it would just fall to the ground. But what happens is that yes, it does try to fall to the ground. It does try, because there is a force, it does get attracted to the Earth. But by the time kind of it makes a movement over here, it's actually because of its velocity, it's being carried over to a different location, right? So it's over here now, right? So it's now moved, right? So this as it orbits the Earth, kind of the orbit looks like this, right? So that kind of falling is, there's also a kind of a movement across. It doesn't kind of do this in reality, right? It's not falling and moving and falling and moving. But every kind of movement towards the Earth, right, it won't really end up here because its velocity carries it over here, right? And at this moment, if it tries to kind of fall towards the Earth, its velocity carries it over here, right? It's moved over here. So this kind of, this may help you kind of understand, yes, it is actually falling towards the Earth, but every time it kind of it tries to move towards the Earth, because it has a speed, it's getting carried over forward, right? If it wasn't for this movement kind of around the circle, it has a tangential velocity, right? It has a velocity that's tangent to the circle. If it didn't have the velocity, it would just fall to the Earth, right? But it's still falling towards the Earth. It's just that every time it's trying to move towards the Earth, it's moved sideways a bit, right? And if it moves towards the Earth, it moves sideways a bit. So it has this dual, kind of two movements, right? Moving towards the Earth and moving around the Earth at the same time. And that's what keeps it going around in a circle, right? And it keeps it in orbit. Another way to think about this is using the idea of velocity, right? So if you think about the velocity vector of the moon, right? Here's the velocity vector. At that moment, the acceleration is in the direction of the force, right? So here's the acceleration of the moon towards the Earth. And what this acceleration does is, because it's 90 degrees to the velocity, it serves to rotate the velocity, right? So every time it gets around, right, the acceleration is always towards the center of the Earth, but what the effect is to make the velocity vector kind of turn around. The magnitude doesn't change necessarily if it's going in a circle in particular, just to simplify. Then the velocity vector's magnitude doesn't change. It's the same magnitude, but the direction of the vector keeps changing because the acceleration is causing the velocity, right? The acceleration causes the velocity to change with time, and that could mean that it's going faster and faster or slower and slower, but it also could mean that the velocity's direction is changing, right? And the effect of this particular acceleration, called a centripetal acceleration, right? We'll see that later. This effect is to change the direction of velocity, right? So the reason why the moon keeps going around the Earth is, yes, there's gravity, right? There's a force. But it's not just that force. The other effect is it has to have some velocity to begin with, right? It has to have a velocity that gets it going in a circle like this. So then the effect of gravity is that it will keep it going in a circle, right? And it is kind of like if you put like a tennis ball at the end of a string and you kind of swirl it around your head. And that is kind of what's happening, right? There is a force, of course, but also there has to be a velocity also. Otherwise, this wouldn't work, right? Okay, so questions about that or questions about midterm 1? Anything that's kind of questions in general? So conceptual questions, you have technical questions, autolock sort of thing, ask away. We'll monitor the discussion. We have several minutes, so we can talk about that. So just to be clear, right, so no friction, no gravity on midterm 1. What you should be able to do is apply Newton's laws, right? So both the accelerating case and not accelerating case, be able to draw a free body diagram, split up vectors, inclined planes, fair game, right? Without friction, of course, but if you had an incline, that's fair game. But yeah, trying to applications of Newton's laws, just generally, without getting into the specifics, no drag, like nothing like that. Yeah. Questions or?
Questions about when the next homework is due?
Good question. I'm trying to figure it out because it's usually Tuesdays and Fridays, but we also have to kind of think about the exams, and then there's a holiday on Thursday. So instead of this Friday, most likely will be the following Tuesday, because you have the exam to work on until tomorrow, and so then there's a holiday on Thursday. So yeah, so most likely it'll be the following Tuesday, and I'll send you a message about it. Other questions? Everybody got on-lock sorted out? No technical issues tomorrow, right? That's the hope. Okay.
A lot of them are asking if there can be another honor lock check today, and how do they access the formula sheet during the exam? Yeah.
So so let's answer the formula sheet. When you open up HonorLock, so I think Aaron made a video, so the HonorLock video assignment thing that's on Quest, you should be able to still access that anytime, I think. If you watch the video, Aaron kind of shows you what the setup looks like once you open up HonorLock, what everything looks like. You can also go on the HonorLock website, right? I sent a link in one of the earlier announcements. Or just Google HonorLock and how to prepare, right? Like as a student, and it'll walk you through what you should expect to see. There's information on their own website where it'll help you prepare of, okay, this is what you expect. The equation sheet shows up at the bottom. Unfortunately, it's not the most obvious place. There's no button that says equation sheet. It's at the bottom. There's exam details, I think, at the bottom. If you click on the bottom, there's a pop-up and there's a link, okay? And yeah, you should be able to access it. Yeah, that's the way you get to that. If you want to get a preview, let's switch to the computer. If you want to preview what you're going to get for the equation sheet, you can see it under Files. If you click on Exams, and then kind of this is what you're going to see on HonorLock, right? So when you're going to see this view, you can zoom in, right? And then this is the view that you're going to have for the equation sheet, okay? There's a lot of questions over the exam. Okay, can you summarize?
Just go down. One of them's asking if they can print out the formula sheet.
Yeah, so some of you have kind of mentioned like it's harder to see. So if it's hard for you to see this, because maybe the text is too small or something like that. I'm okay with you printing this out. However, just make sure it's an actual printout and you're not having your iPad next to you or something like that, right? So you should have one device open during the exam, right? And that should be your computer, and everything else should be put away, right? Your phones, your iPads, your watches, whatever can access the internet, put it away, put it in another room, right? Silent, away from you, right? None of that should be near you. So if you do want to print this out, that's fine. Go ahead and do that. Because some students just have said it's hard to see this or something, and then if it just makes your life easier, that's fine, totally fine to do that.
Another is they're asking about what the midterm is going to consist of, so conceptual, or just equation,
So check out the practice exam, right? So I did send out a deadline for that, but don't worry about the deadline. It's just you need to set a deadline on class. But you can still access it, right? You can view the PDF, you can view the solutions for the practice, get to kind of the idea of what you should be expected to do, right? So I'm not going to hide, there's nothing to hide here, right? I will tell you this is the sort of thing you're expecting. So the practice exam is your kind of, hey, can you do all this stuff? Can you kind of work through problems like this? The practice does have, I think, 1 or 2 questions on friction, so just ignore that. But other than that, it kind of gives you an idea of what you should expect. Right? So there's a few conceptual things, but it's mostly like the homework, right? One of the big things is, unlike the homework, you don't have multi-part questions. It's just one question because just to keep it simple, the number of questions, right? The topics, all on the announcements. So if you're not sure about something, go check out on Canvas. There are lots of, I think maybe 3 announcements about the midterm. Read all of that. It's really, the more you kind of pay attention to all those details, the better it is going to be, right? So I'll just kind of look at the ed discussion after class too, in case we missed anything. Come to drop-in hours today, right? So if you, where are we going? We're do the syllabus here. Drop-in hours for today, right? So right after class, Jericho's here, then me, Aditi, Saba, Patrick, right? Ariana, all throughout the day, right? So please stop by, drop-in hours. Don't hesitate, right? Depending on, we're available throughout the day, right? So come talk to us about anything related to the questions you have, right? Anything else, kind of last-minute stuff that?
Just a lot over just exam, content and
content. Okay, yeah. Let me. I'll browse through the ed discussion after class, just in case I missed something. But again, announcements, right? Just there's a lot of information about the exam, about friction. We talked about honor lock. Mainly this one, midterm 1, important information, right? It is kind of lengthy, but read through it. It's just there to help you, right? So if you read through it, it will be helpful to you just so that you eased into it, right? So just before we go, so everybody's clear, let's switch to the computer. Click on honor lock, right? At this time, tomorrow, right? When we're talking about tomorrow morning, around 8:45, you should be able to do this, right? So we'll kind of ease everybody in. Once you go through the honor lock procedures, you're in Quest, that's when your timer will start, right? So none of the honor locks, taking your picture or IDs, that doesn't count towards your time, right? So take your time, go through slowly, and get that done. So the critical part is do not go to Quest, right? Don't go to Quest directly. What you want to do is, at the time of the exam, click on honor lock, right? And you should be able to access honor lock. At the time of the exam, I'm going to post on Ed Discussion a thread that says, okay, midterm 1 technical questions, post here. Don't email, don't post it into the Canvas inbox, don't do anything, right? So there's one place to post technical issues. If you have any kind of technical thing, I cannot get into the exam, Ed Discussion, I'll send you the link to the post, right? So that's where you want to post it. That makes it easier for us to keep track of all these things, right? If there's any kind of bug, something's going wrong, we can see that, right? And we can address it much faster. So everybody on that thread, right? So one thread. Once you're in honor lock, obviously you won't be able to access Ed Discussion, right? So Canvas, anything, all that stuff will be gone. So then once you're in the exam, you're good, right? You're all set. So carry on. But if you're having trouble getting into the exam, Ed Discussion's where you want to go. Check the thread. post if you have a question. Again, don't email because there's 320 odd students in the class. So if there's all these emails generated, we won't be able to keep up and it's just going to get really messy, right? So just that's one thing. So again, click on HonorLock, right? That's where you start the exam. Don't go to Quest. The exam is on Quest, right? It's like built into Quest. It's from there. But that's not how you access the exam. You have to go to HonorLock first, right? Everybody clear, right? You can repeat this to yourself a few times, right? HonorLock first, right? And the only place to go. All right, so I'll talk to you virtually tomorrow. No class tomorrow, right? Because you're going to be taking an exam. We'll be back on Wednesday, and so see you then.